This is part 4 of section 2.4 for Introduction to Proofs. We are now going to do the last two progress checks. So progress check 222 using a counterexample. So here we have a sentence: for each integer n squared plus n plus 1 is a prime number. So that's saying it's true for all integers n. So to prove that it's not true, you have to find an n that doesn't work. Well, if I try 1 squared plus 1 is 3. Well, that's prime. If I try 2, so that's 4 plus 2 plus 1, that's 7. 7 is prime. If I try 3, I've got 9 plus 3 is 12 plus 1 is 13. If I try 4, 4 squared is 16 plus 4 is 20 plus 1 is 21. Hey, 21 is not prime because it's 7 times 3. So that's our counterexample. Okay, what about for each real number x, 2x squared is greater than x? Now I have to find a counterexample here. Now for most numbers that I tend to randomly pick, this would be true, but when x is very small, very close to 0, then this number will be smaller than this number. So say if I try 0.1. So if I try 0.1, then 2x squared is 0.1 squared would be 0.01 times 2 is 0.02. That's not greater than 0.1. So notice how I line things up. So I've got this thing here, I've got the left side there, the right side there, and we connect them, but with a not greater than symbol. So /0 greater than means not greater than, which you could have also just said as less than or equal to, but I'm trying to emphasize that it's not the case that it's greater than. Okay, so that's how you find counterexamples for false statements. Okay, for progress check 223, we have a new definition. An integer n is a multiple of 3, provided that there exists an integer k such that n equals 3k. Now this should look familiar because we've defined even and odd numbers already. So this is just, it's sort of 3 even, being a multiple of 3. So just like, just want to point out that, when I first taught over even and odd numbers, I used little smiley faces there, just to show you that there just needs to exist a number, and you can use any symbol you want for it. So we're going to write this definition in symbolic form using quantifiers, completing the sentence. An integer n is a multiple of 3, provided that there exists a k in the integers such that n equals 3k. Give several examples of integers, including negative integers that are multiples of 3. Here are some: -6, -3, 0, 3, 6, 9. Give several integers, including negatives, that are not multiples of 3. When you got -5, -4, -2, -1, 1, 2, 4, 5. Now let's use symbolic form in the definition of multiple of 3 to complete the following sentence. An integer n is not a multiple of 3, provided that for all k in the integers, n is not equal to 3k. Okay, so the definition had it there exists an equal sign. So you change the quantifier, you change the last symbol in there. Okay, without using the symbols for quantifiers, complete the following sentence. An integer n is not a multiple of 3, provided that for any integer k, n is not equal to 3k. Okay, progress check 224. Negating a statement with two quantifiers. So here we have this sentence: for all x in the integers, for all y in the integers, x plus y equals 0. So let's write it in English. So in symbol form first. So negating it, so moving a negative past the for all makes it that there exists. Moving negative past the for all makes that one there exists. And then inside here we negate that part. So x plus y is not equal to 0. So there exists an integer x and there exists an integer y such that x plus y equals 0. And that completes section 2.4.